Today's lesson is sourced from Chapter 2 of Mechanics of Materials. This video is part 1 of the lesson, where we'll review the key concept. Stay tuned for part 2 in the next video, where we'll solve an example. We'll start by bridging the gap in our understanding of strain. Now, that's a pretty common word in our everyday language. For example, think about what a strained muscle would feel like in your body. The muscle may have been overstretched so much that it caused some sort of tear or damage to the muscle fibers. Strain in the engineering world is actually a very similar concept. We use strain to measure the amount by which a body deforms. So let's define deformation. Deformation is basically a change in the shape and size of a body caused by a force that's applied to it. Try to theorize ways that a body can deform. Maybe it's caused by stretching, like what happens with a rubber band. Maybe it's caused by excess pressure, like when crushing a soda can. In fact, deformation can even be caused by changes in temperature, like what happens when a plastic water bottle expands in the heat. Strain is a measurement of that deformation. And just like we have two types of stresses, we also have two types of strains, normal strain and shear strain. Let's talk about normal strain. It's basically meant to determine the change in length of a deformed body. If an axial load is applied to a member, the force will either elongate it if it's pulled or shorten it when it's compressed. Again, remember that's tension and compression. Since deformation is almost never uniform throughout a body, we pick a point and generalize the strain to be the average normal strain. The average normal strain equals the change in length over the original length, where epsilon is the average normal strain, L is the new length of the member, and L sub 0 is the original length. Normal strain is essentially a change in length per unit length. So it's technically dimensionless because the length units would cancel out. But it's best to still use units, and we write the units in terms of a ratio of length units. For example, we would write millimeters per millimeter, micrometers per meter, inches per inch, etc. If the value of normal strain is positive, then the body elongated, and if the value is negative, then it contracted. Now let's talk about shear strain. It's meant to determine the change in direction of a deformed body. If we have two line segments that are originally perpendicular but then undergo a change in the angle between them, we can calculate the shear strain. The average shear strain equals the right angle minus the new angle between the line segments, where gamma is the average shear strain, pi over 2 is the original right angle between the perpendicular line segments, and theta is the new angle measure between the line segments. Shear strain is also technically dimensionless because it's written in radians. If the value of shear strain is positive, then theta is now an acute angle, and if the value is negative, then theta is now an obtuse angle. Our last key concept involves the engineering applications for strain. In reality, we can't be having structures that deform a lot, or else we lose stability. That's why most engineering design involves high structural integrity, where only very small deformations are allowed. This is called small strain analysis. For example, normal strain values are much smaller than 1. Shear strain values are also relatively small to the point that the following trigonometric assumptions can be made. The change in angle between the two line segments represent delta theta, and so sine and tangent of delta theta is approximately just equal to delta theta, and cosine of delta theta is about 1. In summary, normal strain is used to find the length deformation, while shear strain is used to find the angle deformation.